Lesson 20 is all about the remainder theorem. So for 20.1, we're just going to talk about the relationship between factors, remainders, and zeros because they all kind of go together. So examine the graph of f of x equals x cubed plus 2x squared minus 5x minus 6. That's the graph below, obviously. So first we're going to find the zeros. That's where the graph crosses the the x-axis. And then we're going to use those zeros to write the function in factored form. So for the zeros, they are, looks like at -3 right there, at -1 right there, and then at 2 over there. So we'll say our zeros are x equals -3, x equals -1, x equals 2. And then to be able to write this in factored form, we have to think about, okay, what factors would, or what linear factors would create these zeros? So like x equals 3. It's always going to be like kind of the opposite of what your like zero is. So if ours is -3, for example, our factor would be x plus 3. But if you ever forget that, the other approach is to just kind of take these little like equations that we have that are like the zeros and make them so that everything is on one side and the other side is equal to like the number 0. So in order to that, I would add 3 to both sides, and then that would give me an x plus 3 equals 0. So then that means that my like linear factor that I would set to 0 to get the solution, x equals -3, would have to be x plus 3. It's just kind of like inverse operations. And then if we use that same approach with the x plus 1, or sorry, x equals -1, I can add 1 to both sides to cancel out the -1, and then that'll give me an x plus 1 over here equals 0. And then for the last one, x equals 2, I would subtract 2 from both sides. That would give me an x minus 2 equals 0. So it's kind of like working backwards, like if we were solving by factoring, we would get these factors, x plus 3, x plus 1, x minus 2, set them equal to 0, and then that would eventually give us the solutions x equals -3, x equals -1, and x equals 2. Okay, so from the graph, though, we find the solutions and we work backwards to find the factors. And then finally, the goal for this part of the problem was to write the function in factored form. So that means that I just have to take each of my 3 factors and multiply them together. So it would be f of x equals x plus 3 times x plus 1 times x minus 2. And then this is my answer for that first part of the problem. So f of x equals x plus 3 times x plus 1 times x minus 2. So now that we see f of x in factored form, like x plus 3 times x plus 1 times x minus 2, if those are the factors, that means that the original polynomial f of x equals x cubed plus 2x squared minus 5x minus 6, it's technically divisible by each of those factors. So what that means is, like, if I were to take this original function and kind of set up like long division or synthetic division like we learned about in lesson 19 and divide by any one of these 3 factors, I would divide it and I should get no remainder. Because if something is divisible by something else, then it should divide perfectly with no remainder. So if we, like, I'll use like kind of a regular number as an example. So let's say like 21, like 2 factors of 21 are 7 and 3. So if I were to take 21 and divide by either 7 or 3, it would divide perfectly and I would have nothing left over, no remainder left over. So that same thing can kind of apply to dividing polynomials. And we're starting to build up to like the remainder theorem, and it's something that we can use to kind of check to see if a polynomial is divisible by a factor without actually dividing. So, okay, so that's what we're building up to. So the next part of this problem evaluate the function at each of its zeros. Sorry, there's some typos, but at each of its zeros by substituting them in for x into the function f of x equals x cubed plus 2x squared minus 5x plus 6. So that's the same function that we've been working with the whole time. So what this means is I'm going to take each of my 3 zeros, so those are these ones up here, x equals -3, x equals -1, and x equals 2. So x equals -3, x equals -1, and then x equals 2. Make sure you leave some kind of space to work between them. And we're going to substitute each of those in for x into the function one at a time though. So we'll start with x equals 3. So if I'm putting that in for x, I'm going to find f of -3 and then put that in here, here, and here for all the x's. So it'd be f of -3 equals -3 to the third power plus 2 times -3 squared minus 5 times -3. I still don't leave myself enough space, really. And then minus 6. I'm going to just bump these over a little bit. And then now we'll just go ahead and simplify with those x equals -3's in there. So -3 to the third power is -27. -3 squared is 9, but then I have to multiply it by 2, so it'd be 18. -5 times -3 is a positive 15, and then minus 6. And then if we add and subtract, so -27 plus 18. So -27, sorry, like mistyped. -27 plus 18 is -9, and then plus 15, 6, and then minus 6 is 0. So all this together ends up being 0, and then we'll just repeat that same process, but with the next like x value that we have, which in this case is x equals -1. So we'll find f of -1. So we'll take -1, put it in for all the x's. So -1 to the third power plus 2 times -1 squared minus 5 times -1, and then minus 6. So -1 went in for all the x's, and then -1 to the third power is -1. -1 squared is +1 times 2 would be +2, and then -5 times -1 is a +5 minus 6. So -1 plus 2 is 1, plus 5 would be 6, minus 6 would be 0. So we got 0 there as well. You could probably maybe guess what we're going to get for the last one also. It's kind of the whole point. But the next one is x equals 2. So we'll substitute in 2 for all of our x's. So we'll find f of 2. So it'd be 2 to the third power plus 2 times 2 squared minus 5 times 2 minus 6. Okay, kind of got it in there. Sorry, it's a little squished. So 2 to the third power is 8. 2 times 2 times 2, and then this is just basically like another 2 to the third power because it's 2 squared, and then times 2 again, so another plus 8, minus 5 times 2, so minus 10, minus 6, and then 8 plus 8 is 16, minus 10 is 6, minus 6 is 0. So for all three, we're getting 0. So I'm taking okay, so let's look at this from what a whole. So we got our zeros, and then we evaluated those zeros in the function. So we had our zeros, x equals -3, x equals -1, and x equals 2. And every single time that we evaluated the function at that 0, we ended up with a final answer of 0, and that's kind of the basis for the remainder theorem. So we haven't even gotten to what the remainder theorem is yet, but that's the fundamental part of it. So don't stress it yet. There's a couple key concepts before we move on to 20.2, and then that's where we actually introduce the theorem. Okay, so these 4 key concepts. The first one, zeros are where the output of the function is 0. So notice but sometimes it's hard because the zeros, sometimes we're referring to the zeros as in x equals a few numbers, in this case -3, -1, and 2, And then like there's also the number 0, so I kind of wish they had a different word. But anyways, the first bullet point, the zeros are where the output of the function is 0. And notice like these are all of our outputs. Like we evaluated the function and we got a final output of 0. And then the second bullet point, the zeros are where the function intersects the x-axis. That's how we actually found those initially. And then third bullet point, the zeros of a function can be used to find linear factors of the function rule. So that's what we did in this section right here, was we took our zeros and we created factors from them, and then we wrote the function in factored form. And then the last bullet point, the factors can divide into the function rule without a remainder in the quotient. So that means that I could take my original function and divide it by any one of these 3 factors, and I would get just like essentially like a whole polynomial out. That sounds silly to say, but like I just wouldn't have that last little part, like the remainder, where I have to write it over what we divided by. Okay, so 20.2, understanding the remainder theorem. So the remainder theorem itself. Let f of x be a polynomial if f of x is divided by the linear polynomial x minus a, then the remainder is equal to f of a. Okay, so that doesn't really have to mean that much now, but in this section I'm going to show you like 3 different ways to find the remainder using like 3 different types of that sounded silly. I just said that really weird. Anyways, I'm going to show you 3 different ways to find the remainder. One is long division, one is with synthetic division, and then the last one is by applying the remainder theorem. We should get the same answer every single time, so keep that in mind. Like you'll kind of have an option to use a certain way and then decide which one you feel like is most efficient. Okay, so find the remainder of 2x squared minus 3x plus 4 divided by x plus 1 using the following 3 methods. So if you haven't watched the lesson 19 video yet, you definitely need to watch it, because that's where we do like long division and synthetic division for the first time. So if you haven't seen that, make sure you go back to it before finishing this. So long division, we're dividing 2x squared minus 3x plus 4 and then we're dividing it by x plus 1. And then there was no, like, we didn't skip any powers of x in this, like 2x squared and then 3x the first power and 4. So I don't need to add any like zeros or placeholders in. So I'm ready to just go ahead and start dividing. So I start by dividing 2x squared by x. That's 2x. So I'm going to put that up here. And then next I take my 2x and I multiply it back through that binomial. So I would do 2x times 2x is 2x squared, and then 2x times 1 is 2x. And then next I subtract this line. This first term in each, always we want it to be exactly the same, because now that we're subtracting, we want them to cancel out. I like to put parentheses around when I'm subtracting to like kind of remind myself to not forget to also subtract the second term and don't accidentally like end up adding it. So 2x squared minus 2x squared, that's 0, that cancels out. And then negative 3x minus 2x is negative 5x. And then next I bring down my like next term, so I bring down the plus 4. And then this is my new first term that I'm dividing into. So I would do negative 5x divided by x is negative 5. And then now that I have a new term on top, I'm going to take that and multiply it back through. So do negative 5 times x is negative 5x. And then negative 5 times 1 is negative 5. And then now that I have that line filled in, I would subtract it. And then if I do negative 5x minus negative 5x, that's 0. That cancels out, and we always want that first term to cancel out. It should also be always exactly what is like above it. These should be the same. And then 4 minus negative 5, so like minus the negative turns into plus. So 4 minus negative 5 is really the same thing as like 4 plus 5, so that would be a 9. And then there's no other terms over here for me to bring down, so that means that this is my remainder. Okay, so if this was just a division problem, we would write our final answer as like, plus 9 over what we divided by, so over x plus 1. So 2x minus 5 plus 9, or so yeah, 2x minus 5 plus 9 over x plus 1. But for this problem, we're just asked to find the remainder. So just my remainder would be 9. And it, like, you don't have to write it as over x plus 1. That's just when you're writing your final quotient. You would write the remainder as like out of what we divided by. But just remainder is 9. Okay, so the next method is synthetic. So the synthetic division is when we draw like kind of like the upside down division box guy. Uh, so we put the coefficients of what we're dividing into inside. So this would be 2, -3, 4. Again, we don't skip any powers of x, so we don't need any placeholders. 2, -3, 4. And then I think when we did lesson 19, I said we need to compare this to x minus k, and k goes here, but sorry, that's the way like I've taught it in the past in previous textbooks, and I made those before I realized that this theorem uses a instead of k, but they have the same exact meaning, so I'm gonna just kind of replace my k's with a's. Just keep that in mind, that it's referring to, it's not k, it's referring to the same exact thing, they're just using a different variable. Okay, so if I'm comparing my like linear factor that I'm dividing by into x minus a, that would mean that since this is a plus 1, a would have to be -1. Because there's already that minus in there. So the a value that's turning that x minus a into an x plus 1 would have to be a -1 because it's like minus -1. This minus is there no matter what. So we'll put a -1 right there. And then for synthetic, the first step is to always bring down the first number. And then I take that number and I multiply it by my a value, which is, so 2 times -1 is -2, and that goes here. And then synthetic's a little bit different in that we don't subtract the columns, we add the columns. So we would do -3 plus -2, which is -5. And then next I would take the -5 and I would multiply it by -1. That would get me a +5, which goes in that next open spot. And then I add that column, so 4 plus 5 is 9. And then remember, with synthetic, it's really important to start on the far right. The far right is the remainder. And then the next number over, when you're dividing, would be the constant. And then the next number over would be the coefficient of x to the first power. So we got the same answer. This is just asking for the remainder, so we don't need to write like my 2x minus 5 and then 9 over x plus 1. I just need to kind of point out the remainder, and it's the same exact remainder as we got with long division, because it's the same answer we got with long division. Okay, and then now is the remainder theorem. So the remainder theorem, I'm going to read through it one more time. So let f of x be a polynomial. It is. If f of x is divided by the linear polynomial x minus a, then the remainder is equal to f of a. So this is saying that we should be able to find the remainder by finding f of a, and a was -1. It's the same thing, because we're comparing what this linear factor that we're dividing by. So let's see, if f of x is divided by a linear polynomial x minus a, that's this part. So that's how we're getting our a's. We're comparing this to this. Then the remainder is equal to f of a. So we take whatever a is, same a, -1. And if I find f of a, so in this case f of -1, it should give me the same exact remainder as every other thing. Like, that is just going to be the remainder when we divide these two polynomials. Okay, so I'm evaluating what we're dividing into. So f of x is 2x squared minus 3x plus 4. I'm just going to go ahead and write that over here so we can see it substituted in. So f of x is equal to 2x squared minus 3x plus 4. And then we're going to evaluate at f of a. So we're going to do f of -1. And that means that I take -1 and I substitute it in for my x's. So it'd be 2 times -1 squared minus 3 times -1, and then plus 4. -1 squared is 1 times 2 is 2. -3 times -1 is +3. And then plus 4, and then 2 plus 3 is 5, plus 4 is 9. So we got the same exact remainder. So that's kind of the purpose of this section, is to see that the remainder theorem works. Like, we applied it exactly as it was written. We evaluated the function at f of a when finding a from this x minus a and what we're dividing by, and it gave us our remainder. It gave us the correct remainder. Okay, so that's the remainder theorem. It can be applied a bunch of different ways. You can even use it to check to see if something is a factor or not. The workbooks use, there's one more section on here, but before we do that, the workbooks use this method of applying the remainder theorem a lot. I personally like using synthetic better. It feels faster, and there's some additional perks you get from using synthetic, so we'll talk about that in 20.3, and then that's the last section. Okay, so 20.3, apply the remainder theorem. The remainder theorem can be used to determine if, sorry for all the typos, I typed this kind of fast, if a linear factor, if a linear binomial x minus a is a factor of a polynomial, in order to be a factor of a polynomial, the quotient of the polynomial and binomial factor must have a remainder of 0. So what that means is that if we use the remainder theorem, so over here, or even if we use synthetic and we get a remainder of 0, that means that the factor that we checked, or the binomial that we checked, is a factor. And again, sometimes just reading math and words doesn't make a whole lot of sense, but once you see it applied, hopefully it's a little bit better. So I'll do example 1, example 2. I'll use one just applying the remainder the remainder theorem, and then one using synthetic. And then there's an extra example where it'll be a good chance to show really where synthetic is helpful. But feel free to pause or stop after example 2 if it's enough information. Okay, so example 1, is x plus 5 a factor of f of x equals 3x cubed minus 7x squared minus 103x plus 35. So the first one, we're going to use the remainder theorem where we find f of a. So we have to compare this factor x plus 5 to x minus a. So again, the negative's in there. So you're like, okay, what a value is turning that x minus into an x plus 5? It would have to be x minus -5. So that means that a is -5. And then from there, we're evaluating the function at f of a. So if f of a equals 0, then yes, it's a factor. And then if f of a does not equal 0, then no, it's not a factor. Because if something is a factor, then when you divide it, you should get a remainder of 0. It should divide perfectly. Like the example that we did with 21 is 7 times 3. And if I were to divide 21 by either of its factors, I would get a whole number out with no remainder. So that's what kind of the basis of this. Okay, so we're going to evaluate the function at f of a. So we'll put -5 in for all of the x's. So it'd be f of -5 equals 3 times -5 to the third power minus 7 times -5 squared minus 103 times -5 plus 35. So to 3, and then negative 5 to the first power is negative 125. And then negative 7, negative 5 squared is 25. Negative 103 times 5 is 515, positive 515 from a negative times a negative, and then plus 35 at the end. 3 times negative 125 is negative 375. Negative 7 times 25 is negative 175, plus 515, plus 35, and then now we can add them all together. So negative 375 and then minus 175 is negative 550, and then plus 515, and then plus 35 ends up being 0. So since we evaluated the function at f of a and we got 0, that means that the factor that we checked, x plus 5, is a factor of f of x. So we say x plus 5 is a factor of f of x. Okay, and then the other, like, you can always use long division to check, but that's like the longest probably process that you can use. The other, like, faster one is using synthetic, so that's what I'm going to do for number 2. So for synthetic, we set up that kind of like open box. The coefficients go across the top. So this is a 2, a 5, and a negative 11. So 2, 5, negative 11. And then we still compare the factor that we're checking. So in this case, x minus 4, we compare it to x minus a. So that would mean that a is just positive 4, because that like minus is already a part of the formula. And that number goes on the outside left. So we put a 4 right here, and then we bring down the first number always, and then I take that 2, and I multiply by 4, and that number goes here. And then I add each column for synthetic. So I would do 5 plus 8 is 13, and then 13 times 4, or I multiply that new number, so 13 times 4 is 52. And then I add each column, so now I'm doing negative 11 plus 52 is 41. And then for synthetic, we start on the right side with the remainder, and then the next number would be the constant. The next number would be the power, or the coefficient of x to the first power. But here I just really need the remainder. So the remainder is 41. So you can even say like r equals 41 if you want to, or you could just highlight it where it is on our like kind of synthetic box. But because it's not 0, that means that, so over here, f of a, that's supposed to say 0. F of a is not equal to 0, so that means that x minus 4 is not a factor of h of x in this case. So we would write our answer as x minus 4 is not a factor of h of x. Okay, so between these two kind of like strategies, you can definitely pick whichever one you feel like most comfortable using. There is a certain case where like probably synthetic makes more sense. And it's this like extra example is just literally copied from your workbook. So if you feel like you're good and you have enough, or this is enough information, you can stop the video here. I just want to show kind of one comparison. So in a problem like this, which expressions are factors of f of x equals x cubed plus 3x squared minus 13x plus 15? Select all that apply. So if we use the first method, so like where we evaluate the function for that a value, then we'd have to do each one of these individually and check every single one, like all 5, and that would probably take a pretty long time. If we use synthetic though, what we have, so if we check a factor that works, what we have left from synthetic is a remaining factor. And it kind of like snowballs from there. So the longest part is going to be just getting it to a factor that works like and does have a remainder of 0. So I'm just going to start at the top. So this one is x minus 3. We're supposed to compare these to x minus a. So for the first one, a would be positive 3. So if I use synthetic, coefficients go across the top. So this is a 1, 3, negative 13, and negative 15. We didn't skip any powers of x, so I don't need to worry about that. I'm going to make this a little bit bigger. So 1, 3, negative 13, negative 15, and then a goes on the outside left. So 3 would go right there. Okay, we bring down the first number 1, multiply 1 times 3, that's 3. Add this column. 3 plus 3 is 3 plus 3 is 6. 6 times 3, 18. And then negative 3 plus 18, negative 13 plus 18 is 5. And then 5 times 3 is 15. So 15 goes right there. And then add negative 15 plus 15, which is 0. That's lucky. So we got it on the first try. Okay, so starting on the far right side, this is the remainder. Coefficient, power of x the first, coefficient of x the first power, coefficient of x squared. Okay, so once we get the remainder of 0, that proves that x minus 3 is definitely a factor. But instead of repeating this exact process for all of these options, we can take what we have left and just begin to factor the problem that way. So what that means is, so this part right here is 1x squared, so x squared plus 6x plus 5. So if I take the original problem, f of x, and I factor it, well, I've already proven that x minus 3 is a factor. So I'm going to pull that out. When I used synthetic to divide out the x minus 3 factor, I got the remainder of 0, so that proves that it's a factor. What I had as my actual quotient is the remaining factor. So x squared plus 6x plus 5 is what's left over from this after I divide out the x minus 3. So that's the next factor. X squared plus 6x plus 5, because if these two are factors of the original, then when I pulled this one out, this is what I have left. Those two times each other get us back to the original problem. And then now, so something like this, x squared plus 6x plus 5, we can just factor that using the factoring method, so we already know. So if I just kept factoring this problem, this is an x minus 3, just bring that down. And then this lead coefficient is 1. So this is B, this is A, this is C. When A is 1, I just need numbers that multiply to C and add up to B. B. So they would have to multiply to 5 and add up to 6. So the combination 1 and 5 would work, because 1 times 5 is 5 and 1 plus 5 is 6. So then the x squared part breaks down into x plus 1 and then times x plus 5. Okay, so from x squared plus 6x plus 5, we can factor that with whichever way we feel most comfortable factoring. It's just a quadratic, but that gives us the remaining two factors. So altogether, the three factors of this function are x minus 3, we already have that one checked, x plus 1, we can check that one, and then x plus 5, we can check that one. Okay, so it's just a different way and a different approach of doing it. because it's definitely like if I were to take each of these like factors and find the a value for each of them and use this method up here, like that would get really tedious really fast. So this is just a different